Hi there, this is your moderator, Lori Dearman with WebAttract, your end-to-end solution provider for webinar demand creation. And you are in the right place for experts reveal strategies for coping with how the internet has changed the equation validation process. In just a moment, I'll be introducing our panel of thought leaders as today's webinar is about hearing from these experts as they discuss their real-world experiences and research about equation use in engineering practices, the practical application of calculations, and the risk posed by the internet, along with possible solutions to finding and publishing validated equations. Today we do have a diverse audience of professionals joining us from 16 different countries and 20 different states and provinces, representing a variety of industries, all here to join the conversation around how the internet has changed the equation validation process. So folks coming up on your screen, we'd like to hear from you. What source do you rely most on for equations or guidance on calculations? So your choices here are the internet or the web, books, journals, colleague, intranet within the company. So go ahead and let us know which one you rely most on. Okay, it looks like we have 31% of folks saying the internet or the web, 54% saying books, 10% journals, 0 saying colleague, and 5% intranet within the company. So very interesting statistics there, and appreciate your weighing in on that. I know it'll be helpful for our presenters as they work through their presentations for you today. Now, the host of today's webinar is Novel, and before we get started, I'd like to turn it over to Claudine Berti, Marketing Director at Novel, who'll take just a moment of your time to officially welcome you and express what she hopes you'll get out of today. Claudine?
Thank you, Lori. I'm excited that Novel is hosting today's webinar on the need for reliable equations in engineering practice. If you're not familiar, Novel is a cloud-based application for engineers that integrates technical reference information with analytical and search tools to deliver answers. Before we get started, however, I'd like to take a moment to share why Novel believes this issue is important. Novel recently interviewed 400 engineers about their equation habits and discovered that performing equations is a frequent part of engineering practice. The study further revealed that the internet is a leading source of finding equations, more so than using internal company resources or conferring with colleagues. Sure, the internet is making equation searches more accessible, but given the abundance of unreliable data on the internet, could the internet be decreasing the validity and potentially impacting the quality of your projects? Today's panel discussion invites you to think about how the engineering community can address the critical issue of finding reliable equation resources. Our panelists will reveal real-world experiences about equations used in engineering practice and possible solutions to finding validated equations. With our users turning to Novel for equations and calculations, we saw an opportunity to pull together an expert panel on this topic. I trust that you'll walk away from this discussion with some helpful and applicable tips on how to avoid the risks posed by using unreliable resources for engineering calculations. And stay tuned to the end of this webinar for more resources to explore and share with your colleagues, including an info page on novel.com dedicated to the topic of equations in engineering practice. I'd like to thank our panelists for their hard work and preparation, and I know you'll find this session productive. Back to you, Lori.
Well, thank you so much, Claudine, for the warm welcome and setting the stage for our featured panel, which is comprised of 3 real thought leaders in this space. Joining us today, we have Carl Jacob, Mirto Zakharov, and Colin Selleck. I'll be introducing each of our panelists in turn as they appear on the webinar. So let's start with our first speaker. Dr. Mirto Zakharov's research has been in the area of microbial biotechnology, especially focused in lactic acid bacteria, their metabolic end products, and their usage in food and pharmaceutical industry. Mirto's current research is focused in wastewater engineering and treatment regarding the recovery of valuable chemicals and nutrients from complex effluent streams. Mirto is an active researcher and an associate member of the Institute of Chemical Engineers, UK. As a result of her work and studies, Mirto uses calculations and equations every day and has published a paper on mathematical modeling, microbial, and product kinetics. As a fierce champion that math is the cornerstone of knowledge and is required across all areas of science, we're pleased to have us joining us from Swansea, UK. Mirto, welcome to the webinar.
Thank you, Lori. It's a pleasure to be here, and I hope we all enjoy the seminar today.
Absolutely. And Mirto, I know we have a lot of ground to cover today, so I'll let you go ahead and get the stage, set the stage with the struggles facing engineers today as they work on calculations across multidisciplinary projects. So over to you, Mirto.
Engineering is a multifaceted, versatile scientific field. It is continuously expanding, embracing many aspects of traditional and classical sciences, from physics to chemistry to maths to biology. Therefore, new fields emerge, constantly calling upon acquiring continuously novel knowledge and applying complex calculation and statistics for interpretation of the continuously gathered raw data. Therefore, projects might be multidisciplinary. For example, the fermentative production of lactic acid does require knowledge both of microbiology but also engineering. The engineers might collaborate with specialists from several fields of close or limited proximity. For example, economists, people who would be doing life cycle analysis, modelers who would be forecasting performances, medical practitioners involved in biomechanics or prosthetics, as well as addressing to various audiences, both in the industry or in the academia or in governmental bodies or institutes. Therefore, they are often challenged by the overwhelming amount of data produced and the complex calculations needed in a short amount of time to provide answers, as well as the high mobility that the contemporary professionals do have to have. So, all these hurdles are resulting from this continuously expanding field and the continuously growing demands. There are great amounts of data that need complex calculations needed for the transcription into meaningful answers. There is limited software choice, as well to mobility and fieldwork that does not allow access to book format of calculation manuals. Furthermore, the internet might be definitely benefiting its users, but however, it has created a whole new range of demands. For example, answering emails very quickly. There is a limitation of spare time, mobility, now there are long-distance collaborations. Therefore, there's more exposure to mistakes and more exposure to misinterpretation of results, which are much more visible to a larger audience than before. So what do professionals or young engineers or individuals working in the field tend to do? Their limited time does lead them to do approximations. So they do rely on their experience or their intuition or in rough calculations that rather than detailed analysis. They as well rely on online resources very often to extract information that possibly might not be that reliable. So they do tend to speculate. Consequently, many non-precise results are given, often having serious costs related to time-wasting effects as well. Back to you, Lori.
Well, thank you so much, Mirto. And I know you're not going to go too far. You've got part 2 of your presentation at the tail end today, so we'll be having you back then. Next up, we have Carl Jacob, and a few words in the way of an introduction for Carl. He's a fellow in engineering and process sciences at the Dow Chemical Company. He is founder of the Solids Processing Lab at Dow, and for the last 30-plus years has worked on a vast array of particle technology problems, with particular expertise in silo hopper design, powder mechanics, pneumatic conveying, particle engineering, and drying. He is past chair of the Particle Technology Forum and recently finished a 3-year term on the board of directors for AICHE. Carl is a chemical engineering graduate of Case Western Reserve University. Carl, it's a pleasure to have you here today. How are you?
Good, thank you.
All right, so without further ado, I'm going to pass it over to you, Carl.
Okay, so let's start with why we might want to use equations. The big thing is oftentimes in our engineering lives, our intuition, while in many cases serving us well, is sometimes misguided or in many cases simply wrong. So an equational or mathematical model or a set of mathematical formulations allows us to basically quantitatively analyze a plant problem. In some cases, our systems are so complex that we're going to have to put a series of equations together in order to really get a firm understanding, because we simply can't measure, in many cases, what's going on with a particular physical phenomena. So my first piece of advice would be to don't guess. It's unfortunate, particularly in my area of hopper design, people tend to need to design hoppers. They hold solids. They don't improve productivity of the solids. They're just a place to hold some material. And the mentality is, it's just a hopper. Unfortunately, very few people realize that there's fundamental science and equations to design a hopper, and so therefore they'll simply guess at a design that might work for mass flow. That is to say, where the entire contents of the bin will flow smoothly out of the hopper. Unfortunately for many engineers, data from Bayer in Germany shows that if you have a 45-degree cone, you have a 0% chance that that hopper will be in mass flow. And the consequences are rather disastrous. This is the consequence of guessing. These are hoppers that have been sort of well bludgeoned by a sledgehammer and other tools, and you can actually see that the flow channels have been significantly reduced as a result of repeated bashings. So clearly we need to go and have a more mathematical, fundamental basis of understanding when we're designing and solving plant equipment and troubleshooting those processes. In many cases, just a simple approach is very valuable. In many cases, we don't need to go to a complex situation, but can rather use a rather simple set of equations and glean a useful result. This would be a belt dryer. There's a fan moving down here on the right-hand side. Airflow is being pushed across the bottom of the dryer. There's a air distribution or sieve plate here at the bottom. And then the gas, typically air, passes through a bed of solids. This could be anything from foodstuffs to polymers, whatever. And operations always complains that this side of the dryer tends to be chronically wet. This arrow is misplaced, unfortunately. And so this part tends to be wet. So we ask ourselves, why might that be? In this case, a very simple analysis allows us to, a mathematical analysis allows us to go ahead and solve the problem. In this manner, one could go ahead and use something very sophisticated like computational fluid dynamics, but in this case, a more simple approach is warranted. If we simply use Bernoulli's equation that basically relates the velocity of the material, of the gas exiting the fan, and the pressure underneath the sieve plate, when we use this equation in conjunction with a pressure drop across that sieve plate, we can now make a prediction as to what the expected gas flow is. And that's shown in this particular chart here, where we see that there, on the side away from the fan, there's considerable more gas velocity, and explains well why on this side of the dryer we're chronically wet. Here I've used two simple equations, well vetted, direct from fluid mechanics or perhaps from Perry's handbook, and you get a very useful result. In some cases, we need to go to more complex systems, and assessing plant performance for some things is just simply too difficult using either one equation or using heuristics or intuitions. In some cases, the process conditions may make measurement difficult: high temperature, high pressure, perhaps a corrosive chemical, for example. The process, unfortunately, isn't like we have in the laboratory where we're working perhaps with flasks and beakers and things like that, but rather is enclosed in a metal pipe. And in many cases, the process dynamics are either too fast or in some cases too slow to make accurate measurement possible. So in this case, we're going to combine a set of equations to help us predict what plant performance might be. Here might be an example. Let's say we have this fluid bed reactor system, which I've shown in the middle of the page. We've got a lot of different processes going on within the context of this relatively seemingly simple flow sheet. So we've got the fluid bed. There's particle changes going on inside the fluid bed. We have attrition, the breakage of particles. We have the reaction, which is sort of desired. We have entrainment of the particles out of the bed to the series of cyclones, which I've designated as C here. In addition, we have fresh feed coming into the bed. And lastly, of course, fines are leaving the system via the second cyclone. And let's say your boss comes in and says, well, what's the equilibrium catalyst particle size distribution in the fluid bed? This is a very difficult question to answer, even for a person well-versed in the art. In this particular case, we need some way to count the particles in each size class as they move through this fluid bed system. And this is done via a series of equations called a population balance, which properly accounts for how the cyclones tend to separate the particles, how material moves out of the fluid bed, what the attrition might be, and lastly, what the particle size distribution of the incoming fresh feed is. In this manner, we can make an accurate prediction and see the dynamics of this system as we move along. And with that, I turn it back over to Lori.
Thank you so much, Carl, and we'll have you back for the Q&A session at the end. And folks, next up we have Colin Selleck, and Colin received his BS and MS degrees in mechanical engineering from Louisiana State University. He began his career at Sandia National Laboratories in Albuquerque, New Mexico, where he developed some of the first computer graphics user interfaces. Selleck also worked on robotics-based radiation inspection systems and 3D geometry sensors based on a structured lighting technique. In 1997, Selleck began consulting with the University of New Mexico's Manufacturing Engineering Robotic Laboratory, performing research in coordinated robot motion, computer vision, simulation-based system realization, optimal grasp planning, trajectory generation, and mobile navigation. Since 2006, Selleck has been a lecturer in mechanical engineering at Binghamton University, where he teaches robotics, measurement, and instrumentation, and senior capstone design. Over to you, Colin.
Okay, Lori, thank you, and welcome to our audience. Thank you for attending this webinar on equations in engineering practice. So Dilbert has a unique ability to convey complex issues in a one-panel cartoon. This one summarizes my talk today. So first, I'd like to go over some of the consequences of design errors. First and foremost, there's loss of life. This is the largest consequence and includes pain and suffering to loved ones and loss of income to families of victims. The second is property damage. This includes damage to buildings, bridges, roads, automobiles, personal property, and earthworks. There's also rework. This includes the redesign and construction costs to correct the design errors. The further into the construction process, the more costly the rework. As an example, in the Journal of Construction Engineering and Management, the mean cost for design errors were revealed to be about 7% of the contract value, so it's not insignificant. There's also legal fees and settlements. This is especially true in our litigious society. And lastly, a tarnished public image. This includes loss of future sales and possible failure of the company. This chart shows the cost to fix a design error. And like a machined part whose value increases exponentially as the manufacturing process nears completion, the same applies to the design process. In the engineering design steps of requirements, architecture, detailed design, verification and validation, manufacturing, the costs increase exponentially the further into the design process one gets. Let's take a look at some of the recent consequences of design errors. First, and this one has been in the news recently, is the GM ignition switch. This is an image of a consulting engineer. He's showing the ignition assembly that has faulty ignition switch. This is from the mechanical testing laboratory at McSwain Engineering in Pensacola, Florida. This is the firm that helped to conduct the engineering investigations and failure analyses that resulted in the GM recall. The recall is due to a faulty switch that automatically turns off the car engine, knocking out power steering, power brakes, as well as preventing the airbags from deploying, all while the car is in motion. GM admits to 13 deaths and 31 crashes, but there may be more. In February of this year, General Motors recalled 2.6 million cars. In addition to this faulty ignition switch, GM is also recalling vehicles for faulty power steering. The total recall is 6.26 million cars, almost as many cars and trucks as it recalled in the United States over the last 4 years combined. Total cost to the company, initially $300 million, then $750 million. Now it's $1.3 billion. And their stock shares have slid 17% in this year alone. So the reason the ignition switches failed was, even though they weren't supposed to, was because the switch indent plunger, which is designed to provide enough torque or pressure to keep the ignition from accidentally turning off, did not supply enough torque. General Motors was aware of this potential problem and holding meetings about it as early as 2005, but decided against fixing it because it would take too long and cost too much money. Whose fault is it? Who has been thrown under the bus? The engineers, that's who. The switch designer and the program engineering manager for the recalled cars are all on paid leave. The next example is the T2 laboratory in Jacksonville, Florida. On December 19th in 2007, 4 people were killed and 13 others were injured when an explosion occurred at this laboratory during the production of a gasoline additive. 4 of the businesses were destroyed. The blast was equivalent to 1,400 pounds of TNT, and debris was found up to 1 mile away. The cause was a runaway chemical reaction. This is an image from the Chemical Safety Board showing a reaction vessel. The company tested the reaction in a small 1-liter laboratory prototype, and then they scaled it up to a 2,500-gallon prototype without proper testing. The scaled-up process resulted in the reaction temperatures increasing from what was seen in the prototype. Unknown to the designers, a secondary exothermic reaction also would occur at these higher temperatures, and this is what caused the explosion. The Chemical Safety Board concluded that T2 did not recognize the runaway reaction hazard associated with the additive it was producing. It turns out that bachelors in chemical engineering do not currently cover this reactive chemical hazard, though this is being addressed by the Chemical Safety Board. I might note that other causes were a single point of failure cooling system. This black jacket you can see surrounding the reaction vessel is a cooling jacket, but it was the only cooling system, and it failed either due to a scale buildup in a valve or a faulty valve. Another design error was in the venting system. This reaction vessel did have a venting system, but the pipe size was too small to allow the pressure to be reduced in time, and an explosion was the result. And the last example I have is Hurricane Katrina. On August 29, 2005, there were over 50 failures of the levees and flood walls protecting New Orleans, Louisiana. The total damage from Katrina is estimated at $81.2 billion, nearly double the cost of the previously most expensive storm, Hurricane Andrew, when adjusted for inflation. The levee and flood wall failures caused flooding in 80% of New Orleans and all of St. Bernard Parish. Tens of billions of gallons of water spilled into vast areas of New Orleans, flooding over 100,000 homes and businesses. Over 1,800 people were killed. The levees collapsed due to a poor design. Weakened soils beneath them became saturated and began to slide. The reason for the naturally soft soil is because it's made up of river silts and swampy peat that has been the bane of builders here for 2 centuries. So you can see the water pushed against the flood wall formed this little crack, allowing water to enter into the ground and making it soggy. In addition, these flood walls were not connected to each other, so that further resulted in a weakness of the structure. Now I'd like to go over the types of design errors. This is thanks to David Brosnan and in his paper, Human Error in Structural Engineering. He defines 3 types of errors and their characteristics and dangers. The first type is bounded rationality. By rationality, I mean the logical thinking mind. This type of error includes thinking inside the box. It has characteristics that it reduces problem complexity, often with disastrous results. And the dangers are that the engineer does not gather and or ignores all pertinent information. The second type is imperfect rationality, which fails to look for new and innovative designs. It has characteristics of the engineer only looks at what has been done before and based on his past experience. And the dangers include that he does not apply basic theorems, equations, and models of his discipline. And the last type is reluctant rationality. The engineer does not want to engage his frontal cortex to analyze scattered and seemingly unrelated information. He jumps to conclusions. Impatience leads to easy and often incorrect answers. He fails to explore all avenues of a design and limits its scope. So these are the types of design errors. Brosnan also goes on to discuss the causes of design errors. Engineers have a troubling tendency, in the words of one researcher, to solve the wrong problem. Engineers sometimes try to fit old, familiar solutions to new technical problems, often without reviewing the most basic parameters. This becomes even more prevalent when the old solution is regarded to be successful. Another failing is ruling out alternative solutions to problems. The engineer has blinders on and has failed to engage in lifelong learning. So the kinds of errors, the kinds of engineering problems that seem to bring forth technical mistakes and poor judgment fall into the following categories. The problem is complex, indicated by more than 2 or 3 different design variables. Strong cues suggest the wrong solution. The focus on simple ideas leads to false solutions. There's too much dependence on using a previously successful solution to solve a similar problem. And lastly, failing to innovate where necessary, especially in this ever-changing complex world. Brosnan also goes on to describe some solutions to these problems. The first one is managing the error. Punishment of those who make mistakes after the fact is neither a successful nor justifiable method of quality control in any technically complex endeavor. We should not attempt to judge someone's character on the basis of their performance at an engineering task. Quality control procedures for engineering work should recognize the kinds of faulty information, thinking, and workplace conditions that give rise to human error. Next are the sources of technical information. As consumers of technical information, engineers should demand higher standards of clarity and usability from publishers of building codes and other complex technical documents. Organizations that publish public safety regulations should avoid constant tinkering with technical standards and strive to produce durable and trustworthy codes written with the actual readership in mind. Rules and regulations should not be changed so frequently and completely that years of experience suddenly become worthless. And lastly, teamwork. Teamwork within the engineering office and with other design consultants should be emphasized over the desires of management to move personnel quickly from one project to another. Engineering managers should recognize the risky personalities in situations that can produce unsatisfactory results. What does one of the preeminent scientists of our time say about equations? One must divide one's time between politics and equations, but our equations are much more important to me because politics is for the present, while our equations are for eternity. And finally, equations are important to humanity as they allow prediction of future events and have led to the technological marvels that we find ourselves in today. So equations are essential for many reasons, not the least of which is humor. And now back to you, Laurie.
Thanks so much, Colin, and we'll also be having you back at the end of our presentation for the question and answer session. Next up, we have Mirto with the second part of her presentation. So back to you, Mirto.
Thank you, Laurie. Now, I'm going to be talking about the use of equations in engineering research. R&D projects are a cornerstone in engineering education, with universities all over the world being the breeding ground. Young engineers are taught research practice as part of their curriculum during the first degree. However, the constantly rising expectation and competitiveness in the global job market is leading more and more graduates to pursue further education degrees, regardless of the rising cost. So many graduates are now pursuing postgraduate degrees combining taught modules with research or solely based on research, such as MScs, MRS, MPhil, or PhDs. So most of the publications coming out now, when most of the results of this research is happening as a result, as an outcome of all these students that they actually doing research within university labs or research within university labs in collaboration with industry. Now, during all this quest for knowledge, the engineers or the prospective doctors in engineering have to acquire a certain area of skills regarding their computational abilities, their analytical skills, good lab practice, health and safety, teamwork. So no doubt the 50% engineers and 50% superheroes. So apart from a good numerical abilities, what do engineers have to have? They have to have as well the ability to judge which is the best equation for them to use in each case. For example, if we would like to model the growth of a microbial culture in a batch reactor with end product inhibition, that means that the microbes cannot grow very fast because during their growth they are producing acids or ethanol. So these substances, while are beneficial for the industry and the economy, they don't allow the growth of the microbes. So it is quite difficult to model such a process. So for example, in this case there are 4 different models to be used. So which one would be the correct one? How we are supposed to be doing that, how we are supposed to be judging which is the best equation to be used, by applying a structured research methodology, following books, following manuals, researching in the published papers in the literature, having a structured way and methodology of identifying our equations. On the other hand, we could just go on and have unstructured research, like simple Google things through the internet or use any other gateway, we might be finding loads of information, but whether this information is going to be relevant is another thing. So why it is so important, why structured research should be important? Because no matter how great data we have, if we have built a wrong model, we're still going to be having wrong results. On the other hand, even if we have the perfect model, if we know how to use the right equations, if our data are wrong, if our first scale calculations are wrong, we will still be getting wrong results. As an example, I'm setting this graph here, which is an example of ambiguity in research. This is from my own personal assays that I have developed for identifying antimicrobial substances in dairy food. Now, the assay, although it's based in good data and hard work, it is a poor model because it has a very limited span of identifying the substance. There is no indication of reproducibility of the results. It's quite crude. It's based on an assumption rather than actual quantification method. Therefore, when the paper was further sent for publication, it was rejected. On the other hand, this is an example of successful research where we do see that in this paper, the filtration characteristics are examined of a complex fluid. The author has managed to convince the readers that he's using structured methodology. He has stated all the basic equations needed to be used to reach his goal, has as well put references in, so therefore both the reviewer and the reader can certify that these are valid equations. And finally, how many times we should be checking our equations and how many times we should be checking our model? Well, regardless what Professor Smith from PhD Comics is saying, there's no actual answer. We need, though, to check it multiple times and be very sure whether it confirms or not our hypothesis. But keep calm. Engineers will save the world. Back to you, Lori.
Well, thank you so much, Mirto. And at this point, I would like to invite Colin back to just walk us through some key takeaways that we'd like you to keep top of mind as you wrap up for today's webinar. Colin?
Thank you, Lori. So the key takeaways for today are: do not work alone on an engineering design problem. Using others as a sounding board helps to reveal the complexities of a problem. Plus, other people have different experiences and knowledge that you do not possess. Always have others validate your work through a thorough review process. A second pair of eyes is always useful. Trust your sources. This means using peer-reviewed information that has been vetted by years of practical use in many applications. Tune into your inner conscience to inform you when something does not feel right. And lastly, realize the importance of keeping abreast of our rapidly evolving technologies by investing in lifelong learning. Plus, keeping the mind occupied and engaged in solving problems leads to a sharp and nimble mind into the elder years. And now back to you, Lori.
Well, thank you so much, Colin. And the fact that we're all here today, I think means we're investing in lifelong learning. And if you would like to continue the learning and continue the discussion, we've got some resources here on the screen to do just that. If you want to go out and like the fan page for Novel on Facebook, there will be some discussion continuing there as well. The Twitter hashtag again, if you'd like it. Novel, another great resource for engineers. And as Claudine indicated earlier in the webinar, feel free to go out and explore Novel's page on equations, and also a white paper authored by one of our speakers, Colin Selleck, on equations in engineering practice. I would like to ask each of our panel members to step back to the virtual podium, if you will, and we'll start entertaining those questions. Now, the first question I see here looks like it might be a good one for all of our panelists, so I think we'll just go round robin. We'll go left to right here, start with you, Carl. And the question is, why bother validating when we have computers and software and ready-made solutions?
Thank you, Lori. I think one of the big things here is that we are assuming that the computer is right, and that's just not always the case. As I think Mirto sort of underscored in her second part, it's garbage in equals garbage out. So just because it comes out of a computer and spits out 8 decimal places doesn't necessarily imply it's based on good, firm, fundamental science.
All right, thank you, Carl. That was well put. Mirto, do you have anything you'd like to add to that question?
Definitely, Carl has summarized everything, and in one sentence he's perfectly right. Validating also, because my background is biomedical sciences, validating also serves as a cross-checking reference, both for your equipment and your computer as well. So it's a way to test your reproducibility of your results. It's a way to test that your lab set or your pilot plan set works and works well enough, so what you're actually producing as results are things that other people can reproduce within the same conditions, so everything you're doing is pretty much valid.
Okay, thank you for that, Mirto, and over to you, Colin.
Yeah, my answer is that similar to what Carl said, computers and software, they're tools that we use, that engineers use to perform our duties, and they don't confer a validation in any sense of the word. And ready-made solutions rarely map onto a real-world problem. Given the complexity of our world, it is impossible to have a ready-made solution for every problem. Back to you, Lori.
Okay. I've got a good question here for you, Mirto. And John's asking, Mirto, can you elaborate on validation versus checking of results?
Yeah. Okay. Well, checking the results would be repeating, for example, one experiment and seeing your numbers are correct, right? So you kind of cross-checking that what you've written on your paper or on your spreadsheet is correct numerically. However, validating is the next stage, that you incorporate in your raw data in some sort of of an equation. All right, so for example, Carl's spoken about Bernoulli. I've spoken about models of microbial growth kinetics. Let's take the example of Jerusalemsky. So if I am putting my numbers wrong in there, or if I'm not using the right equation, I'm developing a wrong model. I'm developing a whole different set of results that are wrong. So I do have to go back and validate once again and read once more, reconfirming that I'm using the right models for the right set of conditions.
All right. Thank you, Mirto. This one for you, Carl. Tarek is asking, isn't Bernoulli equation for incompressible fluids? It was used for a gas in one example.
That is true in this particular case. However, I will add, in this case, the pressure here changes very, very little. So essentially, the fluid is of constant density. Across that dryer, there's only about an inch of water difference in density. So essentially, it is it's acting in many ways like an incompressible fluid.
Okay. Well, thank you so much. And at this point, I'd like to go ahead and ask each of our panel members to leave us with just some final comments for our audience. I'll start with you, Carl.
I guess it's more a word of caution, is that just because it's out there on the internet, it doesn't necessarily imply that it is necessarily correct. In many cases, the internet can be our friend. There's a lot of information out there that's at our fingertips that's easily accessible, and the key is to just make sure that the sources are behind the data are vetted and in good use. I had an example the other day where I was looking at a ternary vapor liquid equilibrium, and I was sitting at my dentist and I dialed something up on my phone, which is incredibly easy to do. Fortunately, in this case, it was a very nice little program. I got what I needed, and then I looked at the source that the data was based on, which was the Dortmund Data Bank, which is something that most chemical engineers would very much trust for VLE-type data. In this case, even though the tool looked pretty simple and was very accessible right at my fingertips in the dentist chair, I was able to be confident that the answers I was getting were real and well-placed.
Thanks so much, Carl. And how about you, Mirto? Anything you'd like to leave our audience with?
Work in teams. I think trying also to research and validate your equations and your results by yourself, but also taking advice from colleagues or your line manager or your supervisor is also beneficial.
Thank you very much, Mirto. How about you, Colin?
Yes, well, I would like to say that the internet is a double-edged sword. There's lots and lots of information available, and also it's very easy to search for that information, but anyone can create a web page. So as engineers, we need to trust our sources, which for us means journals, textbooks, and technical reference manuals.
Okay, well, thank you. And you know what? One more question slid in here. So for you, Colin, and Jim's asking, sometimes management thinks engineers have analysis paralysis. What is your advice for engineers to achieve the proper balance for upper management?
Analysis paralysis. I have not heard that before. Does that mean we're stuck too much in the analysis loop? Okay, sure, Carl, go ahead.
I've seen it many times over the course of my career where people will analyze something to death, and the people are waiting. They have the gun loaded. It's like, come on, guys, fire the gun. But yet more analysis gets done. In many cases, some people have a difficult time coming to an actual decision, and it's a balance, and I think it's a learning process for young engineers, both young and old. To me, the one that I think is perhaps more bothersome are engineers, and I think Mirto and Colin alluded to it, engineers that end up being myopic. They end up focusing on just one piece of data at the expense of all the other pieces of data that are at your hands in order to solve a problem, and then consequently wrong decisions get made. That to me is much more worrisome.
Well, thank you so much, Carl. And folks, we are just about at the top of the hour, and there were a number of great questions. Thank you so much. If we didn't get to your question, you can expect an answer via email within a week. Before we do sign off, I'd like to thank each of you for joining us and trust you found today to be of value. And of course, special thanks to Mirto, Carl, Colin, and our sponsors, Novel. As mentioned, you'll receive a short survey at the end of the webinar, and if you take a moment to fill it out, we would greatly appreciate it. Also, a quick thank you to our logistics producer behind the scenes, Terry Holland, for her collaboration and support. Most importantly, thank you for joining us and participating. And as your moderator, this is Lori Dearman saying have a great rest of the week. Bye for now.